Twin functions. Do there exist two functions, f and g, from the set of real numbers to the set of real numbers, such that for any two distinct numbers, say x and y, where x is not equal to y, the following inequality holds. The absolute value of x minus f of y plus the absolute value of g of x minus g of y must be greater than 1 for all x and y where x is not equal to y. Give this problem a try. Pause the video and figure out your approach. The answer is that no such pair of functions exists. To explain why, let's assume that the functions f and g satisfy the given inequality, which is the absolute value of f of x minus f of y plus the absolute value of g of x minus g of y is greater than 1 for all distinct x and y. If such functions existed, we could construct a one-to-one map from the set of real numbers to the set of ordered pairs of rational numbers. This would imply that the set of real numbers is countable, because the set of ordered pairs of rational numbers is countable. However, we know that the set of real numbers is uncountable, and this creates a contradiction. Therefore, the assumption that such functions f and g exist must be false. Next, we will explain how to construct this one-to-one map. The diagram below shows how the function h takes a point x from the real line and maps it to a pair of values, f of x and g of x, in two-dimensional space. Now let's take a look at what the enforced bound tells us about the distance between h of x and h of y. To understand this, we'll need to quickly review some basic ideas from calculus. Take a moment to carefully read the following explanation. In view of this inequality, we could see that h of x and h of y are separated by motes with a radius of root 2 divided by 4. You might be wondering how this could lead to a contradiction. Feel free to pause the video and think about it for a minute. The key point here is that the rational numbers form a dense subset of the real numbers. Consequently, the Cartesian product of rational numbers is also a dense subset of the Cartesian product of real numbers. This means that we can always choose a rational point q of x within each mote centered at h of x. Since these motes are separated, q of x and q of y are not the same when x is not equal to y. We have obtained the one-to-one map from the set of real numbers to the Cartesian product of rational numbers.